Imagine a rock is kicked off a bridge with a horizontal speed of 3.50 meters per second into water that is 8.00 meters below. We'll answer the following two questions. How far does the rock move horizontally before hitting the water? And what is the speed of the rock when it hits the water? We need to remember that when a projectile is launched with horizontal velocity, that horizontal velocity is going to remain constant. Gravity only acts in the downward direction, so the projectile is only going to experience an acceleration in the downward direction. We can see in this diagram that the object starts with no downward velocity, and as it travels along its trajectory, its downward velocity is getting larger and larger. What we'd like to solve in this problem is the horizontal distance traveled from launch point to hitting the water. We'd also like to know the speed of the object when it hits the water. That's going to involve two components, the constant horizontal velocity and the downward velocity that is caused by gravity. It's important in this type of problem to keep the vertical motion and the horizontal motion separate. Again, in the vertical direction, we're going to see an acceleration caused by gravity. We know that's going to be negative 9.8 meters per second. In the vertical direction, it's also important to note that the initial velocity, v0, is 0. This is a horizontal launch. There's no upward or downward velocity to start. I like to add subscripts to differentiate between the y direction quantities and the x direction quantities. The other thing to note in the vertical direction is that the initial position will be 8 meters if we count the water as position 0. I'll write that as y subscript 0, positive 8 meters. In the horizontal direction, it's important to note that the acceleration is 0. Gravity only acts in the downward direction. The horizontal velocity of this rock is going to be constant. We can say that its initial velocity is 3.50 meters per second. It's also correct to say that the constant velocity is 3.50 meters per second. It's not going to speed up or slow down. In terms of the initial position in the x direction, we can really choose it, but it's easiest just to say that it starts at x position 0 and it's going to move from there. I've noted here the two important equations that we're going to use, the position equation for accelerating objects and the velocity equation for accelerating objects. We need to make sure that we apply the correct quantities in the vertical and horizontal direction. The first question we wanted to answer was actually involving the horizontal direction. We wanted to know how far horizontally is the rock going to move before it hits the water. That's going to be based on two things, the speed of the rock in the horizontal direction, which we know is 3.50 meters per second, and the time it's in the air. On any projectile problem, the time that it's in the air is dictated by the vertical direction. We're going to have to solve for flight time before we know how far the rock moves horizontally. Let's use the position equation for the vertical direction. Instead of calling position x, I'm going to call it y because we're working in the y direction. I'm building from this equation here. The first term is 1/2 at squared. That's half the acceleration times time squared. Half the acceleration is negative 4.90 meters per second, 4 meters per second squared. This next step is very important. The initial velocity term. We're talking about the vertical direction. You might be tempted to plug in 3.50 meters per second. If we did that, that would mean that it was kicked upward 3.50 meters per second. So when we're dealing in the vertical direction, this term is 0. We leave it out of the equation entirely. What's left is the initial position. Again, we're working in the y direction, and the initial position is that 8 meters above the water. The position that I'm interested in looking at is when the position of the rock equals 0. That's when it hits the water. So I'm going to set this equation equal to 0. From there, all I need is some simple algebra to solve for t. I'm going to subtract 8 meters from both sides of the equation. I'm going to divide through by negative 4.9 meters per second squared. And And I'm going to take the square root of both sides of the equation to solve for t. And we find that t equals 1.28 seconds. If you follow through with the units on the left-hand side of the equation, you do end up with units of seconds. Now we know how long the rock is in the air before it hits the water. We'd like to know how far it moves horizontally, so we go back to the horizontal side. Let's use the position equation to calculate the position of the rock horizontally when it hits the water. I'm going to use this equation here, and I'm going to leave it in terms of x, because here x is horizontal position. The first term in the position equation is 1/2 at squared. We need to remember we're looking in the x direction, so the horizontal acceleration is 0. We don't need the 1/2 at squared term at all. It equals 0. The next term in the position equation is the initial velocity. We already said that the rock starts with a velocity of 3.50 meters per second. And we also know that's not going to change. It's going to stay at 3.50 meters per second because there's no acceleration in the horizontal direction. Next, I need to plug in the time that I solved in the previous step, 1.28 seconds. And then again, it's easiest to just say that the initial position is 0. So here, all we need to do is take 3.50 meters per second and multiply by 1.28 seconds. Notice seconds will cancel. The horizontal distance traveled is 4.48 meters. So while the rock drops 8 meters vertically, it moves just under 4.5 meters in the horizontal direction. So we have the answer to our first question. The rock moves horizontally 4.48 meters before hitting the water. We did have to find the flight time of 1.28 seconds first to answer this question. We'll tackle the second part of this question in the next video in the playlist. You should be able to click on that in the end screen. Thanks for watching.